My classroom. In this model we have been discussing about energy balance. We have seen the thermophysics and thermochemistry introduction in the previous lectures. Please go through them. We have derived Cp minus Cv equal to our Mayer equation also we have derived in the previous lecture. I hope you have completed that. So also in the regular class we have seen energy balance in crystallizer, and we have considered in that heat of crystallization, all that, right? So now what we are going to do is, in this lecture we are going to discuss about energy balance in various systems. Okay, so energy balance, when we say energy balance, it is applicable for various systems like cyclic process, non-flow process, flow process, like that. Okay, so if we consider the energy balance equations, we have seen in the previous lecture, so how to write the energy balance equation. So overall energy input, overall energy output, so how to write them, what are the different heats that you have to consider, the like sensible heat, latent heat, heat of mixing, heat of dissolution, heat of crystallization, like that. Also if combustion is involved, what is the heat associated with the combustible reactants, and in energy output we will consider heat associated with the combustible products, all that. Okay, so also whatever is the heat added to the system, that is considered as energy input, and whatever is the energy removed from the system or energy lost to the surroundings, that is considered as energy output. So that way you can easily write the energy balance by considering total energy input to the system and total energy output to the system. So if you look at this energy balance in cyclic systems, what is a cyclic system? In a cyclic process, the system is brought back to its original state after a series of changes. So even though there may be temporary changes in the state, but it is brought back to its original position. The energy exchange between the system and the surroundings occurs through the mechanism of heat and work, since these are the energies in transit, right? So work is done on the system by forces acting from the surroundings, and heat is transferred between the system and the surroundings during the process. Since there is no change in the internal energy of a system in a cyclic process, from first law of thermodynamics we have that summation of work done is equal to summation of heat, okay, or heat added to the system. If W is the work done by the system, okay, so we have to take into consideration of Q is negative when heat is rejected by the system, W is negative when the work is done on the system. Okay, if both are measured in consistent units, then we have summation of work done equal to summation of heat added or removed. Okay, so that is the energy balance equation for a cyclic system. Okay, so and if you look at the energy balance in non-flow systems, okay, so we can make use of first law of thermodynamics for non-flow system, and we can write that summation of total energy of the system is equal to change in kinetic energy plus change in potential energy plus change in internal energy. And if we consider this change in kinetic energy and potential energy are negligible, then we have delta E surrounding equal to minus Q plus W. Therefore from first law of thermodynamics we have delta E of system plus delta E of surrounding is equal to 0. So making use of all this, we can write change in kinetic energy plus change in potential energy plus change in internal energy is equal to Q minus W. So if you are considering a steady flow, non-flow process in which there are no kinetic energy change or potential energy changes, so this equation can be simplified to delta E is equal to delta U is equal to Q minus W, right? So even we can do a model example where internal energy at one condition is given and internal energy at another condition is given, but if it is mentioned that heat is added to the air until the internal energy is increased to certain value, we can calculate the heat transfer to the system. It is mentioned that tank is rigid, the volume of the gas does not change during heating, right? So under constant volume, the change in internal energy is equal to heat supplied to the system. So you can determine Q equal to delta U. So U1 initial minus U2 final internal energy will give us the answer of 100 kilojoules. Which by substituting the values we can get the answer easily. Okay. And if you are looking at the adiabatic system, for adiabatic system, in an adiabatic system we know that there is no heat interaction between the system and the surrounding, that is dq equals 0, because the work done or heat is means the work is done fast, that is even there is volume change, volume is quickly changed, pressure change, the pressure is quickly changed, so that way there is no heat loss to the system. So it is a fast process. When I say adiabatic process, it is a fast process. So the dq is equal to 0, so we have du equal to minus dw equal to minus pdv. So for adiabatic reversible process, right, we can say that pressure and volume in adiabatic process are related by pv power gamma equal to constant, where gamma is the ratio of cp by cv. Okay, so and cp by cv is constant for an ideal gas. This ratio gamma is constant for an ideal gas. Also we have seen Mayer's relationship, cp minus cv equal to r. So using that we can write what is r equal to cv into gamma minus 1. So we can see that dw equal to pdv, which is equal to cv dt minus cv dt. So the work done in an adiabatic process is given by this equation, dw equal to minus cv dt. So if we are integrating it, so we can get w equal to cv into delta t, that is t1 minus t2. So we can substitute again cv value. If you want to eliminate cv value, we can express in terms of r, and we can simplify to get the equation that t2 minus t2 by t1 is equal to p2 by p1 by power gamma by minus 1 by gamma. Okay, so if you look at the energy balance in the flow system, so we have mechanical energy. I think in fluid mechanics course also we have derived Bernoulli's equation, and in thermodynamics also it will be covered. The energy balance in steady state flow process is important when we are considering the flow of the fluids like pump, fans, compressors, turbines, heat exchangers, reactors, etc. So here the energy is transferred or is converted from one form to another form. So if you are considering an idealized flow system, you consider a fluid is flowing through a apparatus like from a section 1 and 2, where we have a heat exchanger and a turbine. The heat added to the system is Q and work done on the turbine is W. So typically what happens when you are having hydrothermal power plant, right? So we can have a section 1 and 2 at different height, Z1 and Z2. So let the internal energy is U1, volume is U1, volume is V1, pressure is P1, Z height is datum level is Z1 and velocity is U1. Similarly at section 2 we have U2, V2, P2, U2 and Z2, where U is internal energy, volume, pressure, velocity and datum level. Okay, so the total energy of the fluid entering and leaving the system is made up of the internal energy possessed by the molecules, right? So the potential energy due to its elevation above the datum level, the kinetic energy due to the velocity of the fluid, and the flow energy which is equal to the product of pressure P and the specific volume V of the fluid. So if we apply the between section 1 and 2, what is the change in total energy of the unit mass of the fluid? So we will get delta U equal plus delta PV plus G into delta Z plus half into delta U square, right? That is velocity, small u. Okay, so capital U is internal energy, small u is velocity. So we had delta capital U plus delta product of PV plus G into delta Z plus half into delta U square. Using the first law of thermodynamics, this should be equal to what? Q minus W, right? So heat added to the system and work done by the system to the surrounding. The energy imparted to the fluid externally through the heat or work, right? So substituting that, we can simplify it to get this expression delta H plus G into delta Z plus half delta U square equal to Q minus W. Once we have this equation, we can go for deriving the mechanical energy balance. The total energy balance considers only the input and the output from the system. So for fluid mechanics calculation, it is customary to express this equation in the form of mechanical energy balance also into account. Okay, so the mechanical energy balance takes irreversible effects such as fluid friction also into account. So we can derive this expression by starting from the definition of enthalpy. What is that? D capital H, D capital U plus PdV plus VdP. So starting from this, by substituting, by using the first law of thermodynamics, and for reversible process the work done by the fluid is dW equal to PdV. Okay, we can modify this to write this equation. Okay, so we can obtain this mechanical energy balance using your thermodynamics. Okay, so applying all the thermodynamic property relationships, we can arrive at this equation. But finally we can take into account the work loss due to reversibility also. Okay, so once we consider that, we will get this expression. So this mechanical energy balance equation is used for energy balance in flow system. Okay, what is Bernoulli's equation? It is nothing but a special case of this energy balance in flow system. Okay, so this Bernoulli equation is an special form of energy balance in flow system where we consider non-viscous fluid where this F becomes 0, and for incompressible fluids volume is independent of pressure. Okay, so that way, and there is no shaft work exchange with the surroundings. In that case, we will get a Bernoulli's equation, P by rho plus G into Z plus U square by 2 equal to constant. Okay, so for that we will make use of this total energy balance, that is the mathematical statement of first law of flow process, that is delta H equal to G into delta Z plus half delta U square is equal to Q minus W. Making use of this and applying du values, dw values, when you consider changes in kinetic energy and potential energy are negligible. Okay, so and finally if you take into account the work loss due to reversibility, you get this mechanical energy balance. And when mechanical energy balance is considered for a non-viscous and incompressible fluid, we get Bernoulli's equation. Okay, we will solve some numericals on energy balance. We have derived the how to write, we have derived the energy balance equation. How to write the energy balance equation we have seen in detail. So we have considered a evaporation column where you have a feed and we have supply heat steam to it, and the evaporate is coming out and products is coming out, and the steam also comes out as condensate. So we have seen what is the energy material balance we have already done. So what we have additionally considered is heat associated with the feed stream HF. Heat associated with the steam is capital HS, and the heat associated with the condensate is small hs, and the heat associated with the evaporate is capital He because it is in vapor phase, and the heat associated with the product is small hp. So with that we have written energy balance. We have seen that, just recall, refer to that video, previous lecture video, and go through it how we obtain this energy balance. Okay, so we have energy balance equation is F into HF plus S into lambda S equal to E into He plus P into HP, and we have defined each term. And also we have seen that how to determine the heating area. Heat transfer area required for heat transfer can be calculated once we obtain the S value. Once we have S value, the heat lost by the steam is equal to heat gained by the evaporator system. So we have UA delta T. This U value is given. We should be able to solve this problem. So once we have S value, we can determine the heat transfer area required for this required evaporation operation. Okay, so that we will make use of these equations to solve the numericals. Okay. Okay, so we will solve a problem. Take down this problem. An evaporator is to be fed with 5000 kg per hour of solution containing 10% solute by weight. The feed at 40 degrees Celsius, the feed at 40 degrees Celsius is to be concentrated to a solution containing 40% by weight, of the solute under absolute pressure of 1.03 kg per centimeter square. Okay, steam is supplied, steam is available, steam is available at an absolute pressure of 3 atmosphere. Saturation temperature is 134 degrees Celsius. The overall heat transfer coefficient is is 1500 kilocalories per hour meter square degree Celsius. Okay, calculate heat transfer area that should be provided. Number 2, steam requirement. Okay, let it be A, B. So this is the question given. So we should be able to solve it. So actually some data are also given. Some data are given. Treat the solution as pure water for purpose of calculations. For purpose of enthalpy calculations, and some data are given. Temperature, enthalpy in kilocalorie per kg, for vapor as well as liquid is given. So data is given at 40 degrees Celsius. Temperature is in degrees Celsius. Okay, so temperature is 40. At 40 degree, values are given 613.5, 40.5. Then we have 100. So for 100, the values are 613, 639.2 and 100. And at 134, values are 651.4 and 134.4. So this is actually data to be taken from reference table. For simplicity, it is given here directly. Okay. So this we have to consider. This data is given. Okay. So these are the data given in the question. So you can start solving this problem. Okay. So how to start solving? So what you should do? So you should draw a diagram first, right? So draw a diagram and note on this thing. First step is draw a block diagram and label the given values. Okay, so what is our basis? Our basis is feed containing 5000 kg. F equal to 5000 kg per hour of solution. Okay, so that is our feed. So we can make a neat diagram. So we have one system. So we supply steam here, right? Remember when we are drawing for material balance, we did not bother about what is happening, right? With respect to steam. But whereas when you do this energy balance problem, we have to consider that also. So we have feed given F equal to 5000 kg. Let XF be the heat associated with it. Okay. Then it is liquid, so we can say HF is the heat associated with it. And we have evaporate. We have evaporate, and the heat associated with it is He. So we have products. So products P, mole fraction is XP. Sorry, mass fraction is XP, and heat associated with this is small hp because it is in liquid state. It is a concentrated liquid, right? So it is a dilute liquid. We have concentrated liquid. So this condensate steam we have, and steam temperature is given. Okay, so steam temperature is given like 134 degrees Celsius, and we have condensate here. Okay, so we can write the overall material balance. So what is overall material balance? If you write material balance, so we have taken a basis. I write it here again. Our basis is 5000 kg per hour. Okay, so we have F equal to E plus P is the material balance. When we write material balance, we don't consider the steam here, right? So they don't come in contact with each other. So F equal to E plus P, we can say E equal to F minus P. So F data is 5000, E equal to 5000 minus P. Okay. Then what is the energy balance? So energy balance is we have to consider S, right? How to write energy balance? It is the heat associated with it. So F into HF plus S into lambda S. When I write lambda, it is I am taken into consideration of here steam input and steam output. Okay, lambda S is equal to HS minus small hs. Remember the heat here is HS and the heat here is small hs. So that a difference in this is lambda. Okay, where lambda is equal to this. So this you refer to previous lecture if you want more details. So heat associated with the evaporate is E into capital He plus P into small hp. Okay, so these are the equations which we may be using in this solving this problem. Okay, so what are the other data given? So other data given is xf equal to given 0.1, 10%, right? So that is 0.1. And similarly xp is given 40 percentage, so that is 0.4. So we can substitute this individual material balance, right? Individual material balance for solute is xf into f is equal to xp into p. So which you can it use it to determine the value, right? So using this material balance equation 3, these data, so what is the data? This a, this b, and this c. Substituting a b c in third equation, so what we get is x of 0.1 into 5000 is equal to 0.4 into p, which will give us the value of p is this much kg per hour. How much is your calculator? So what you have is 0.1 into 5000 divided by 0.4 equal to 1250. Are you getting that? 1250 kg per hour. So let it be ABC and D, and D in second equation, D in equation 2 gives us D in equation 2, this is equation 2. So substituting P value, okay, so what we get is E equal to 5000 minus 1250, which is equal to, is a calculator, 5000 minus 5000, 3750. So we get E value equal to 3750 kg per hour. Okay. So from energy balance, we can find the steam value. As I said, to find steam requirement, so here we have all the data. F we know, HF we know, lambda S we know, E we know, HE we know, P we know, HP we know. So only unknown parameter is S. Okay, please proceed to solve this problem to get S value. S equal to what? So how to write this HF value, that I will tell you with this given data. Okay, so this here data is given. With this given data, we should able to write what is our HF value, all that. Okay. So what we have to, so one thing we should, I told you repeatedly, is we'll use small h for liquids, capital H for vapor or gases. Okay. So with that in mind, we can write the data. Okay. What is our capital H means vapor, small h means liquid. Data at the temperatures are given. What is required, that only we have to choose. Okay, to confuse there may be additional data. So what we want, that only we will take. Okay, so what is given? An evaporator is fed with 5000 kg of solution containing 10% by solute by weight. The feed is at 40 degrees Celsius. So heat associated with it is 40.5 or 613.5. It is 40.5. So that way you remember capital H or small h. For vapor, capital H. So if it is capital H, we want to take data. This is small h. Okay. So now correspondingly what we want is HF. HF is at 40 degrees Celsius. The feed is at 40 degrees Celsius. So we can write HF equal to 40.5. Okay. Any doubt in this? HF equal to kilocalories per kg. Understood? So similarly, what is lambda S? We can write lambda S also. I'll go there. Lambda S is equal to HS minus small hs. What is capital HS? Steam is entering. What is the steam temperature? We know steam temperature is, steam is entering at 134 degrees Celsius. It is given steam is available at this temperature. So this is your HS and this is your HS, small hs. Okay. So if you substitute, we get lambda. This is more important. It won't be given directly, means how to get it. Okay, so at this temperature we have enthalpy data is here, so we can get lambda S value equal to 651.4 minus 131.4, which is equal to 651.4 minus 134.4 is equal to 517. So we have lambda S equal to 517 kilocalories per kg. Okay, so let us mention A, B, C, D. Okay, let it be E, let it be F. Okay, so what else we need? So we need values of HF we have determined, lambda S we have determined. We need HE, evaporate. Evaporate will leave at what temperature? 100 degrees Celsius, right? So water evaporation will take place at 100 degrees Celsius. Okay, so we'll take that it is vaporization is taking place at 100 degrees Celsius water. So that way 100 degrees Celsius, what is it is capital HE, right? So this is our capital HE. So we can write capital HE is equal to, so remember what we have written? We written HF value, lambda S value, and now HE value. HE is 639.2 kilocalorie per kg. Let it be G. Okay. Then what is HP value? So product is leaving, but still that also will be at 100 degrees Celsius, right? So that way we will have small HP value equal to 100 kilocalories per kg. Okay. Small HP value is 100 degrees Celsius, but it is liquid. So enthalpy value is 100 kilocalories per kg. Let it be H. Okay. Now we have E, F, G, and H. Use substituting EFGH value in this energy balance equation. EFGH value in energy balance equation. So we have give a number to this. Substitute EFGH in 3. So what we get is, and also the values of F. Okay, so values of F, F, E and P we have to substitute. So okay, we will substitute the value of P and E also. So I wrote D1, D2. What we have taken as F value is A. Substitute the value of F here. Substitute the value of D1, D2, E, whatever we have mentioned. Okay, so we are actually substituting the values of F, HF, S, lambda S, E, HE, P, and HP. You will get S value. We simplify to get the value. What is the value of S? I'll just, for people who are unable to follow, I am writing it so others can proceed to get the S value. Okay, so F value is 5000. Heat associated with it is 5000 kg per hour into 40.5 kilocalorie per kg. So what we get is finally all we will get in terms of kilocalorie per hour. Okay, so substituting in this equation, what we get is 5000 multiplied by 40.5 plus S into lambda S we have determined. S into 517 is equal to 3750 into 639.2 plus 1250 into 100. Okay, so this is the only unknown parameter. Simplify to get the value of S. S equal to this much. Steam, no, it is again kg. Yeah, S is in kg per hour. This is in kilocalorie per kg. Okay, so the S will have a unit of kg per hour only. Okay, so what you get is, what do you get? 4486. 4486 kg per hour is what we get S value. Okay, so once we have S value, so what we can determine is we know the heat transfer, right? Q equal to UA delta T, which is equal to S into lambda S. Okay, so that is the heat balance. Okay, heat balance in the system is, so we have steam, we have liquid. Okay, heat transfer is taking place between steam and the liquid. Okay, so only heat is being transferred from here to there. Here heat is gained, here heat is lost. Okay, so steam, whatever heat is given by the steam is the heat gained by this one. So what we can, S value we have, lambda S value we have, A value we have to determine now. Second part is determine A. U is given, right? Delta T, what is delta T? It is the temperature of the steam minus temperature of the liquid. Okay, liquid means that is the system. Okay, so what is delta T? Delta T is the temperature of the steam minus temperature of the liquid. So we know that liquid is at 100 degrees Celsius operation temperature. Steam is available at 134 degrees Celsius. So it is 34 degrees Celsius is the delta T. Okay. So U is given. What is the value of U given? U value in the given question, it is given. What is the value of U? U is 1500 kilocalories. So we have U value equal to 1500 kilocalories per hour meter square degree Celsius, right? Okay, so now substituting, you will get the cross section area, interface heat transfer area. Heat transfer area is equal to, what is that? UA delta T equal to S into lambda S. So A is equal to S into lambda S by U delta T. Substituting, S value is, what is your S value? 4486 kg per hour into lambda S value is 517, right? Kilocalorie per kg divided by U value. Heat transfer coefficient is given 1500 kilocalories per hour meter square degree Celsius into delta T is 34 degrees Celsius. Check. So what you will get is answer in meter square. Okay, this is your calculator. 4486 into 517 divided by 1500 divided by 34 equal to 45.47. 45.4757 like that it is coming. So we can say that around it is 45.5 meter square. Okay. So you can write the answer in the sentence. The steam requirement is, the steam requirement is 4486 kg per hour. Answer for first part. B part is the heat transfer area required is 45.5 meter square. Okay, so that is the solution. We'll do one more numerical. Take down. It is desired to concentrate it is desired to concentrate 5000 kg per hour of a solution of sodium hydroxide from 10 percentage to 25 percentage solids in a single effect evaporator. Steam is available at 110 degrees Celsius and the vapor space maintained at 410 mercury. The boiling point of water corresponding to the vapor space pressure is 84 degrees Celsius. Okay, the solution has a boiling point elevation of 10 degree Celsius. The enthalpies of the feed and thick liquor are 90 and 80 kilocalorie per hour, kilocalorie per kg respectively. And the enthalpy of the vapor is 650 kilocalorie per kg. The feed enters at its boiling point corresponding to the vapor space pressure. The feed enters at its boiling point corresponding to the vapor space pressure, and it is given lambda s. Okay, lambda s equal to, how to insert lambda? Lambda s is equal to 534 kilocalorie per kg. Question is calculate the steam consumption per hour. B part is, if the available heat transfer area is 35 meter square, estimate the heat transfer coefficient. Okay, estimate the overall heat transfer coefficient. In the previous problem, heat transfer coefficient is given. We have calculated the available area. In this problem, we have to determine the overall heat transfer coefficient, but area is given. Okay, so it is decided to concentrate 5000 kg. So 5000 kg per of solution of sodium hydroxide from 10 to 25 percentage. Steam is available at a temperature of 110 degrees Celsius. Okay, so vapor phase is maintained at a pressure. So according to it, we have a boiling point, and there is boiling point elevation data given. Boiling point elevation is 10 degrees Celsius. The enthalpy of feed and the thick liquor are given. Enthalpy of vapor is also given. Okay, so now we should be able to solve this problem. Okay, how to start? I think it is similar procedure only, so you should be able to do it yourself. Please proceed. So how to proceed? So make a diagram. Okay, so you should draw a diagram. Evaporator. So first to draw a make a basis. What is the basis? Basis is 5000 kg per hour of feed is given. XF is also given. XP is also given. So we know material balance F equal to E plus P. Okay, and we know individual material balance XF into F equal to XP into P. Okay, we can write E equal to F minus P. Okay, substituting the data given. What is XF percentages are given, right? 10 percentage to 25 percentage. 0.1, 0.25, right? So 0.1 into 5000 is equal to 0.25 into P. So substituting P and C into, we get the value of P. Okay, so P value is, what is the P value? You'll get around 2000. Check, because it is 500. 500 divided by 0.25, 2000. So you'll get P value 2000 kg per hour. Substituting C in equation 3, we get E value. 5000 minus 2000 is 3000 kg per hour, right? Evaporation value is this much. Okay, now steam conditions are given. I'm just writing that. Steam condition is, what is that? TS is given 110 degrees Celsius. Lambda is given 534 kilocalorie per kg. What is vapor space condition? Vapor space condition is given that P is 410 mm mercury. Temperature is 84 degrees Celsius. And HE value is 650 kilocalorie per kg. The corresponding values are given. Okay. So if it is not given, we have assumed to be 100 degrees Celsius. At atmospheric pressure, it is 100 degrees Celsius. Here we are having absolute pressure. Lower the pressure, we are going to have change in boiling point, right? So these are the conditions, and it is also given that boiling point elevation is taking place in this one. so it is not negligible. Boiling point elevation is 10 degrees Celsius. Okay, and liquid temperature, so liquid temperature is, so the liquid temperature is equal to TL equal to the vapor space temperature 84 plus 10. Okay, so there is temperature increase. So 94 degrees Celsius is the temperature at which the product liquid stream is leaving. Okay, so feed enthalpy data is given, right? So corresponding values we can write down. So HF data is given. How much is HF value? HF value is given that 90 kilocalorie per kg. Okay, and thick liquor enthalpy is also given. HP is given. So refer to the question. All these data are given. Okay. So HP is equal to 80 kilocalorie per kg, and we have determined the values of P and E already. So we can write in the energy balance equation. What is the energy balance equation? F into HF, energy balance equation, F into HF plus S into lambda S is equal to E into capital HE plus P into small hp. Okay, so the data, all the data are there. So what we have to substitute? We have to substitute to get the value of S. Okay, so if we substitute the value, what we have is, even you can rearrange here. What we have to do is S into lambda S, we can rearrange to write S into lambda S is equal to P into HP plus E into HE minus F into HF. This lambda can go to the right hand side and we will get the value of S. Okay. So what is the value? S into lambda S you get, and substitute to get S value. Okay. So lambda S value is 534. So if you get the value, whatever is the product value, S into lambda S, you write that value. S into lambda S you will get. Substitute and get the values. Okay. So even we'll make a substitution here. What is it? So P value, what is P value? It is 2000 into its HP value is 80 plus 3000 is the E value into its value is 650 plus, sorry, minus feed is 5000 into its associated value is 90. Okay, so if you substitute, you are going to get the value. Okay, so finally you will get S value. This value I'm writing 1.66 into 10 power 6 kilocalorie per hour, right? So if you substitute here, divided by lambda S value, so we get S value equal to around 3110. Okay. Yes, what is the value you get? We'll cross check it. 2000 into 80 plus 3000 into 650 minus 5000 into 90 is equal to 1.66 into 10 power 6. That is correct. Divided by 534 equal to 3108.61. 3108.614. So that way you can skip those values. Okay, so we get steam value equal to this much kg per hour. Okay, so now what is the second part? So that is the answer for A part. Steam requirement. is 3108.6 kg per hour. Okay, so what is B part? You know that Q equal to UA delta T, which is equal to S into lambda S. Why we kept S into lambda S? To make use of it readily here. That is the reason I kept it here separately. S into lambda S value. Okay, so what we have is S into lambda S value, so that we can substitute here readily. Okay, so what we have is A is here, it is data given is area is given to be 35 meter square, and what is delta T? Delta T is T of the steam minus T of the liquid, so which is liquid temperature we have seen. Remember last problem what we did is T of L is equal to vapor temperature. Both were 100 degrees Celsius, 100 degrees Celsius. Okay, but in this problem it is at absolute pressure is different. Okay, so we are having a particular absolute pressure and we have considered boiling point elevation. So when there is boiling point elevation, temperature of the liquid equal temperature of the vapor plus temperature of boiling point elevation. So we have 84 plus 10, 94, right? So that is the value. So temperature of the liquid is 94. Steam is available at a temperature of 110 degrees Celsius, right? So this is important. This is the difference between previous problem and this problem. So what is the value? 16 degrees Celsius. Okay, so we have Q. Now A is known, delta T is known, S into lambda is known. So only parameter is U, unknown parameter. So U equal to S lambda divided by A delta T. Okay, S lambda is 1.6 into 10 power 1.66 into 10 power 6 divided by area is 35 meter square. You can write with the unit also. This is kilocalorie per hour. This is meter square into delta T is 16 degrees Celsius. So unit of your U value will be kilocalories per meter square or degree Celsius. Okay, so all unit, nothing is getting cancelled. We have the unit of this for overall heat transfer coefficient. Overall heat transfer coefficient is how much? Use the calculator. 1.66 into 10 power 2, 3, 4, 5, 6 divided by 35 divided by 16. So what you get is 2.96 into 10 power 3, that is 2964.3. 2964.3. Okay, so you can round it. So you have to round it because when you are talking in this 1000 values, we can say 2964 kilocalories per meter square or degree Celsius. Okay, this is more than 0.5, we can round to next number. Less than 0.5 means less than 5, we round to previous number, right? So that is why we have rounded our answer to this value. Okay, so in this we have solved two numericals. In first case we have not considered the boiling point rise. In the second case, boiling point rise data is given, that is 10 degrees Celsius there. So that the main difference what we raised, we have to consider the liquid temperature to be temperature of the vapor plus temperature of the boiling point rise. Okay, so that together will gives us the temperature of the liquid product. Okay, so liquid product temperature is equal to temperature of vapor plus boiling point rise. So this important point was considered in the second numerical. So and we got the answer for the steam requirement as well as overall heat transfer coefficient is determined. Okay, if you have understood the concept, please leave a comment. Thank you for joining my classroom. If you have any doubts, please contact me.